Good afternoon to all. Myself, Dr. Pritee Raotole, Associate Professor, Member of Board of Studies of Kavaitri Bahinabai Chaudhary, North Maharashtra University, Jalgaon, Head of the Department of Physics of Mahatma Gandhi Shikshan Mandal's Dada Saheb Dr. Suresh G. Patil College, Chopra, presenting here the effect of variation in synthesis temperature on corrosion resistance characteristics of the polyaniline-co-o-toluidine coatings. Conducting polymer is a class of advanced materials and it having the outstanding properties and wide range of applications. It having several advantages like lightweight is
Ma'am, click on the next slide, then only it will be visible. Only
okay,
first slide is visible now. Yeah,
now is it
now it is
visible?
visible.
Okay. The class of conducting polymer is a class of advanced materials. It having the outstanding properties and wide range of applications. And these conducting polymers having the several advantages like lightweight, easy to synthesize, environmental friendly, effective for the corrosion protection, and inexpensive. We have used the electrochemical synthesis route for the synthesis of these conducting polymers because it is simple, relatively inexpensive, no need of oxidant, direct formation of conducting polymer films, easy to control, environmental friendly, doping is simultaneous and can perform in situ spectroscopic studies. Also, the quality of film is good by this method. However, there is a limitation and availability of conducting polymers due to the exclusivity of the monomers. To overcome this problem, different synthesis approaches can be attempted. First approach involves the synthesis of substituted derivatives of conducting polymers on oxidizable metals. Second approach, use of copolymerization to prepare the new polymers with inbuilt tailor-made properties suitable for the application. Third approach involves the bilayered composite coatings. The objectives of the present work are to synthesize the electrochemical copolymerization of aniline with O-toluidine on low carbon steel from aqueous media, to evaluate the performance of these copolymer coatings against the corrosion of low carbon steel in aqueous 3% NaCl solution. Moving forward in it and synthesize the PaOT5 copolymer coatings at various synthesis temperatures and to study the corrosion resistant characteristics of PaOT5 copolymer coatings synthesized at various temperatures. In experimental details, the coatings were synthesized by cyclic voltammetry by sweeping the electrode potential from minus zero point -5 to 1.5 volt at the scan rate of 20 millivolt per second. The corrosion protection performance of these coatings was evaluated by the potential dynamic polarization measurement by sweeping the electrode potential from minus zero point -25 to 0.25 at the scan rate of 2 millivolt per second in 3% NaCl. We have synthesized the polyaniline, polyO-toluidine and copolymer, that is the combination of this polyO-toluidine and polyaniline in the ratio of 50-50 concentration. So that is treated as PaOT5 and compare the potential dynamic polarization measurement results of these three types of coatings and which its results reveals that the copolymer effectively protects the LCS and improves the corrosion protection efficiency than that of offered by the corresponding homopolymers. The homopolymers are polyaniline and polyO-toluidine. So by taking these previous results as a reference and moving forward in it, the POT5 copolymer coatings, which effectively protects the LCS and synthesize this POT5 copolymer coatings at a different synthesis temperature like 60 degrees Celsius, 40 degrees Celsius room temperature, 15 degrees Celsius and 0 degrees Celsius. The first scan of cyclic voltammogram of this POT5 coatings characterized by three anodic peaks Anodic peak A attributed to the dissolution of low carbon steel electrode surface and formation of iron tartrate passive layer. The oxidation peak B corresponds to the oxidation of monomer, and the current density of oxidation peak B is higher for the when it is synthesized with the temperature 60 degrees Celsius. The anodic peak C assigned to the oxidation of tartrate electrolyte. A careful examination of the first scan of cyclic voltammogram represents that the area of anodic peak A of PaOT5 copolymer differs significantly depending on the synthesis temperature, and it follows the order, it having the highest value for 60 degrees Celsius and lowest value for 0 degrees Celsius, while for room temperature it is having the intermediate intensity. This shows the second scan of cyclic voltammogram of POT5 copolymer coatings at various temperatures. The cyclic voltammogram of second scan reveals noticeably different characteristics. The anodic peak A corresponding to dissolution of low carbon steel is not observed here. So and also the current density corresponding to the oxidation peaks are observed to be increased during the second scan, which indicates the growth of the POT5 copolymer coatings. After second scan, the current density corresponding to anodic peak decreases gradually, which indicates the formation of noble coatings. Here this graph shows the variation of intensity of peak C with the change of synthesis temperature. And it again follows the order like the peak A in previous slide. It is having the higher value for 60 degrees Celsius and lower value for 0 degrees Celsius, and all other values are in between of these. So at high temperatures such as 60 degrees Celsius and 60 degrees Celsius and 40 degrees Celsius shows the higher current densities of the oxidation peaks, which results in over-oxidation of monomer, reveals in its degradation. So however, at room temperature, the current density of same is intermediate, but at lower temperatures such as 15 degrees Celsius and 0 degrees Celsius, the current densities uh, does not shows expected oxidation and reduction behavior, so the peaks are depressed. Here we can observe the scanning electron micrographs of POT5 copolymer synthesized at various temperatures. The scanning electron micrograph of 60 degrees Celsius and 40 degrees Celsius shows the thick black coating with the pores and cracks on it due to the over-oxidation of monomer. However, at room temperature, it shows the uniform poreless coating, and at lower temperature, that is 15 degrees Celsius and 0 degrees Celsius, very thin and featureless morphology. The evaluation of corrosion protection performance of POT5 copolymer synthesized at various synthesis temperature in 3% NaCl was evaluated by this potential dynamic polarization measurement, and these results shows that the corrosion potential at higher temperature as well as lower temperature negatively shifted, and also the corrosion rate increased than that of the room temperature. So it indicates that the corrosion resistant characteristics of the coating are better when it is synthesized at room temperature. Now the conclusions of the present work are: the aqueous sodium tartrate solution is a suitable medium for the electrochemical copolymerization of aniline with O-toluidine on low carbon steel. The potential dynamic polarization measurement reveals that the POT5 coatings effectively protects the low carbon steel, and they have higher corrosion protection efficiency as compared to that of the corresponding homopolymers. The POT5 coatings were successfully synthesized by cyclic voltammetry at a different synthesis temperatures. The cyclic voltammetry and ACM results reveals that the decay in properties of POT5 coating occurs when it is synthesized at high temperature due to the over-oxidation of the monomer. However, at lower temperature, it does not give expected oxidation and reduction behavior. So very less amount of polymer was deposited with the lower growth rate and resulting very thin and non-adhesive films. The corrosion-resistant characteristics of resulting coating was investigated by potentiodynamic polarization techniques in 3% NaCl, and the potentiodynamic polarization measurement reveals that the PaOT5 coatings synthesized at room temperature effectively protects the low carbon steel against the corrosion than other synthesis temperature in 3% NaCl. Thank you.
Uh, Myself, Dr. Amol Manake, Assistant Professor in the Department of Chemistry, Pratap College of Mamer, situated in the Maharashtra. My presentation topic is the synthesis and characterization of cadmium sulfide nanoparticles. Recently, we synthesized in the laboratory the cadmium sulfide nanoparticles using a different methodology. We work on the different methodology. And initially, why I going for the nanotechnology? Because nanotechnology is a very, very wide and very big branch, which refers to the which is a branch of the science, and which is devoted to the designing and producing and using the structured devices and systems by manipulating the atoms into the range of 1 to 100 nanometers. And that's why I'm going for the nanotechnology. There are the various applications. There are various applications of nanotechnology, cell bioimaging, detection of cancer, drug and vaccines. They are used as in a biosensors, also used in a transistors and semiconductors, nanoscale material, which incorporated in the care products like a titanium oxide, which is nano tubes, nanoparticles used in a recently used in a sunscreens, nanoscale films like which are used nowadays used in eyeglasses. Nanotechnology also goes to the surface treatment of fabrics, and it is a various nanoparticles are obtained as an antioxidant. These are the various methods to synthesize the nanoparticles. Uh, First one method is the biological method, second is the physical, and third method is the chemical method. In biological method, there are also various sub methods: fungi method, bacteria, yeast, and plant products. In the physical method, there are also various branches: thermal method, explosion method, evaporation method, pyrolysis method. And in chemical method, soil gel method, condensation method, reduction method, and precipitation method. We go with the chemical method in sub criteria. Precipitation method is there. By using the precipitation method, we synthesize the cadmium sulfide nanoparticles. This is the abstract. Nanomaterials are, everyone is knowing the nanomaterials are the leading edge of the nanoscience and nanotechnology. To found the efficient method is a big challenge in nanotechnology. Herein we develop a green method to synthesize the cadmium sulfide nanoparticles. The cadmium sulfide nanoparticles were synthesized by ultrasonication method using sodium sulfide and various salts of the cadmium. In this work, we use the various salts of the cadmium for the synthesis of the cadmium sulfide. Current synthesis saves the considerable energy which is essential for the formal synthesis. The synthesized nanoparticles were characterized by UV, visible, XRD, and HT analysis. This is the preparation method. Preparation of cadmium sulfide nano. First, we in one beaker we take the 2.60 gram of cadmium sulfide, pure cadmium carbonate dissolves and making that 0.1 molar solution. In another beaker we take the 0.78 gram of the pure sodium sulfate. Also there is a 0.1 molar solution. Both the solutions are mixed. Not vigorous mixing, dropwise mixing is there. After dropwise mixing, we put we maintain two pH years, one acidic pH and basic pH. We got the both results from the both medium, acidic medium as well as the from the basic medium. And after addition, we placed the beaker into the ultrasonic bath sonicator for the 1 hour. Then the cadmium sulfide fine nanoparticles are formed. Then we filter that. Then that nanoparticles will be filtered using the Wattmann filter paper number 41. Then after washing, uh, I see the lots of methods are lots of researchers use the cadmium sulfide nanoparticle synthesis, and they calcinate the cadmium sulfide nanoparticles for the 6 to 7 hours. But by using the ultrasonic bath sonicator, there is no need to go for the 6 hours drying in oven. Only 15 to 20 minutes are essential for the drying of the product. There is no water molecule is there in the product. Uh, we also go for the doping. We are not only prepared cadmium sulfide pure nanoparticles. We also go for the doping. We dop the cadmium sulfide nanoparticles with the 1% Mg metal. And that is the processor, and this is the bath sonicator we use for the synthesis. We also varying the pH. Already told that we use the two pH mediums, acidic as well as basic medium. Both samples, both cadmium sulfide nanoparticles were characterized, and we found the better difference between the acidic and basic medium nanoparticles. We did the X-ray diffraction, XRD study. From the XRD study, it is confirmed the formation of cadmium sulfide nanoparticles in different methods. The XRD pattern exhibited diffraction peaks at the 26.4 degree, 30.7 degree, 51.6 degree, which refers to the cubic structure and perfectly matches to the standard data of the cadmium sulfide nanoparticles. The crystalline nature was significantly observed, and that was also calculated at the end. It was observed that the diffraction peak in the presence of doping agent is broader than the pure cadmium sulfide nanoparticles. This result confirms that the crystalline size of the cadmium sulfide nanoparticles. These are the two XRD uh, graphs of the cadmium sulfide nanoparticles. Figure A indicates the pure cadmium sulfide nanoparticles, and figure B, 1.B indicates the cadmium sulfide nanoparticles with the 1% Mg doping. We also take the UV visible spectra. Further characterization of the cadmium sulfide nanoparticles was confirmed by the study of the optical properties. The yellow color powder synthesized and the UV visible spectra were recorded by scanning in the range of 200 to 700 nanometer. The UV visible spectra of the yellow color powder shows absorption maxima between the wavelength 400 to 500 nanometer. It shows in the both spectra due to the resonance band of the cadmium sulfide nano. Due to doping of the Mg, nanoparticles shows the more optical density as seen in the spectra. The figure 2b, in the figure 2b, we can see the optical density is more than in the figure 2.a. Then we go for the HT analysis, simultaneous thermal gravimetric analysis. This TG analysis was conducted to study the quantitative composition of cadmium sulfide nanoparticles. Figure in the next slide. For pure cadmium sulfide nanoparticles, the curves exhibit two distinct slopes. There is no initial weight loss between the 30 to 300 degrees centigrade, means no physically adsorbed water is present in the synthesized pure cadmium sulfide nanoparticles as well as Mg doped cadmium sulfide nanoparticles. This also confirms that pure and crystalline nanoparticles are obtained and no need to be calcinate under high temperature. Only loss of molecules with the low molecular weight and weight loss between the 400 to 500 degrees centigrade indicates the complete stability of the cadmium sulfide nanoparticles towards the heat. The whole weight loss of the pure cadmium sulfide as well as Mg of cadmium sulfide over the temperature range of the 30 to 800 degrees centigrade was
Dr.
about.
Amol, sorry for the
Yes, sir.
interruption. Please wind up within 2 minutes.
Yes. Uh, Only weight loss is only 22.45 and 20.40 7%. This is the STA spectra of the pure cadmium sulfide nano. Here we can clearly see the delta Y, which is 22.45, means it is the total weight loss of the compound. From the 100%, only 22% of the weight loss is there, and showing the very good thermostability. This is the spectra of the cadmium sulfide nanoparticles with 1% mg doping. Here is also only 20.47% of the weight loss. These are the various results, and these are the various salts we use: cadmium sulfate, cadmium iodide, cadmium carbonate, cadmium chloride, and cadmium nitrate. So many salts we use, and so many work is going on, sir, in the acidic as well as basic medium. The work is in progress. Also, we are trying the 1% dropping. In this paper, we are trying with the 1% dropping, but we also go for the 2%, 5%, 10%, as well as we go for the copper, calcium, cobalt, and nickel. These 5 metals we are now use for the doping. Crystallinity and the crystalline size is also calculated for the 2 samples, and it is seen the very good results. From the conventional method, there is a 37% crystallinity of the product is obtained, but while using the ultrasonication method, the crystallinity is obtained at the 64.74%, and the crystallite size is also reduced while we use the ultrasonication. This is a conclusion. We synthesize the stable and pure cadmium sulfide nanoparticles by using the ultrasonicator. It is found that the color and property of the compound is also good. We also tried at the different pH value. STA study also shows that the product is stable to heat. Morphology and structure of the synthesis nanoparticle confirmed by the XRD. UV spectra shows that the different optical density, and in case of Mg dop, there is a increased optical density, and most important is the much more amount of the energy is saved by using the ultrasonication method rather than the formal synthesis. Thank you, sir.
Good evening to one and all present here. My name is Jyoti Prakash, and I am from Shulin University. And the topic of my presentation is electrocatalytic and photocatalytic green hydrogen generation by economical Zn substituted cobalt ferrite. My paper ID is 101. So, first of all, I would like to discuss the current needs and limitation in hydrogen production. So, why we need hydrogen? We need hydrogen due to the reducing fossil reserves and increasing energy demands due to increase in technological demands. And there are also the sustainable development goals that we have to keep in mind. For that, we need a source which is green and doesn't cause any pollution. Hydrogen fits the perfect for this description. Hydrogen can become a decentralized energy source because it can be produced from anywhere. It also has zero carbon emission, and it can also show highest calorific values. It is also easy to use and store. But there are some limitations which must be addressed for hydrogen before we can fully utilize it. First of all, mostly currently the hydrogen is produced by steam reforming. The steam reforming itself requires use of fossil fuel, which defeats the purpose of using hydrogen as a green source. That's why people are using novel methods like electrocatalysis and photocatalysis to counter these limitations. So, in electrocatalysis, we utilize a specific catalyst to enhance or accelerate the electrochemical reaction, which in turn increases the yield of hydrogen production through electrolysis. For photocatalysis, we use a specific catalyst which could be activated in the presence of light and produces electron, which reduces the H2O into hydrogen gas. Both of these methods could become fully green if we utilize the solar energy or another type of energy to power them. So in our case, there are different type of catalysts which could be used for both electrocatalysis and photocatalysis. So we have used spinel ferrite based catalyst for the hydrogen production, both for electrocatalysis and photocatalysis. So spinel ferrites are magnetic oxide having general formula of MFe2O4, where M is a divalent ion and Fe is in a trivalent state. The diagram for spinel ferrites is shown in the figure here. Here we can see that spinel ferrite have two
Sorry,
interstitial.
sorry to interrupt. Your slide is not moving.
Sorry.
Currently, which slide you have?
On third slide, sir.
Yes, but you have to start.
Is it moving now, sir?
Yeah, green hydrogen production approach.
Can you see the diagram, sir?
Yes, yes, yes.
Okay. So here in the diagram, we can see that spinel ferrites have two interstitial sites, octahedral and tetrahedral sites. The spinal ferrite show moderate band gap, which is suitable for photocatalysis, and they are also chemically stable and show higher mass to volume ratio for electrocatalysis. That's why we are going for the spinal ferrites. There are different kinds of spinal ferrite which could be produced, but we have used Zn substituted cobalt ferrite for both electrocatalysis and photocatalysis due to its appropriate band gap and stable chemical behavior. For preparing the sorry, sir, but I think there is some problem and I cannot show my slide. So I will present it like that. Okay. So here is the sol gel autocombustion method, which I have utilized for preparing the spinal ferrites. In this method, we use citric acid as a chelating agent and metal nitrates as starting precursor for preparing the solution. After going through the solution phase, we prepare the gel phase. The gel phase is prepared using ethylene glycol. But before that, we have to maintain the pH using ammonia solution at 7. After adding the ethylene glycol, we get the gel formation, which is then heated to get starting the autocombustion reaction. After that, we get our final product, which is grinded and calcinated to attain the phase purity. So to check the structural integrity of our sample, we use certain analysis to check whether the produced spinel ferrite is of pure phase. We have utilized XRD, Raman, FSM, and EDS analysis to check the structure of our samples. Here in XRD, we can see that at lower zinc doping, there is an impurity phase hematite present at around 33 degrees of theta. But with increasing dopants, doping concentration, we have attained a pure phase. Similarly, for Raman analysis, all the 5 expected Raman band are presented for spinal ferrite. And for FSM, we can see that agglomerated structure is formed and a uniform distribution of particle size can be seen, showing that a pure grain size is formed. Using EDS analysis, we can see the presence of all the desirable elements within the samples, and there are no extra impurity present in the sample. So from structure analysis, we calculated that the crystallized size of the sample was found to be increasing, going from 35 to 42 with increment of the dopant. For case of lattice parameter, firstly, there was no increase in lattice parameter with doping going from 0.02 to 0.04. But at higher concentration of dopant, the lattice parameter was found to be increased slightly to 8.37628. Similar kind of trend was obtained for the Hoping lens. For hydrogen production through electrocatalysis, we studied the Teffel slope and also studied the potential with current density to check whether it is electrocatalytic active or not. For our sample, it was found that with increment of dopant, the value of Teffel slope goes on decreasing, which is a result we require because low Teffel slope shows that it requires lower overpotential to achieve the electrocatalysis, and it also shows faster electrocatalytic reaction, making it suitable for hydrogen production through electrocatalysis. For producing hydrogen through photocatalysis, we see that at lowest of doping, there was only 11.76 millimole per gram of catalyst hydrogen production in 8 hours. But with increment of doping, the value increases to 21.51, showing that our doping was positively influencing the hydrogen production for both photocatalysis and electrocatalysis. So, all in all, we can say that currently the hydrogen production through photocatalysis and electrocatalysis is not so high, but it could be improved significantly by using different catalysts and doping. And spinel ferrite can also harness visible light for efficient photocatalytic water splitting reaction. It was also shown that spinel ferrite have higher activity for both OER and HER performances, but for future, we should aim to enhance the photocatalytic and electrocatalytic hydrogen production efficiencies uh, by checking through different doping, nanostructuring, and hybrid system integration, such as formation of composite. For future work and optimizing the composition and scalable synthesis for enhanced HER and OER properties is required. Thank you.
Good evening, everyone. I am Konica Roy from Tejpur University, working under the supervision of Dr. Shyamul Kumar Das. The topic of my presentation is development of a rechargeable proton energy storage device utilizing gel electrolyte. So as we know, the production of carbon emission is increasing with the increase of energy consumption. So people are moving towards renewable sources of energy like the biomass, wind energy, solar energy. For like adequate energy supply at any moment of time, we need energy storage devices. So for that we need batteries. So coming to batteries, lithium ion batteries, like they rule the whole market, but there are some disadvantages of lithium ion battery, like it is very expensive due to the availability of lithium resources. It is the lifetime is very less, it can catch fire easily. So people are moving towards alternative ways, like they are moving towards aluminum ion battery, zinc ion battery, sodium ion battery. So we are focusing on non-metal energy storage, non-metal charge carrier, that is the proton, or we work on ammonium ion battery. So proton, what are the advantages of proton? Proton are very highly abundant on the earth crust. The molar size of a proton is very small, so it can be used for low very light batteries, and the radius is very small. So for the insertion of the charge carrier in the electrode material, it is very helpful to have a very low hydrogen hydrated radius, and it runs on a very unique mechanism, that is the Gaussian mechanism. So like there are three important components of a battery: the electrode material and the electrolyte. So the electrode material, the cathode and anode, for that we have used transition metal oxide. And for the transition metal oxide, like they have various advantages, like it has they are very easy to prepare, and they have very high theoretical capacity. Most importantly, they have many uh, like their valencies, they have multiple valencies. So for the cathode material, we have chosen V10O24.12H2, that is the hydrated vanadium oxide, and it we have prepared it using a simple hydrothermal method, and it is evident from the XRD that it is in the monoclinic phase, matching the JCPTS number, this one. And it also matches the Raman shift, and it forms a flex-like structure, which is evident from the FSM image. So for the electrode preparation, we have taken PVDF as the binder, NMP as the solvent, and VOH as the active material, and coated it in the 80:10:10 ratio in a conductive current collector, and we have used graphite for that. So for the electrochemical investigation, we did the CV in 3 different electrolyte, taking the same proton concentration in 0.5 molar of H2SO4, 1 molar of HCl, and 3.75 molar of H3PO4. And this is the CV profile. Here, this is showing the redox activity in the reduction. Here, it is showing reduction in the discharge mode. And this one is the charging mode, where anodic peaks are showing that the protons are coming out of the electrode material. So in the 3 electrolyte, it is more of a like showing the same kind of behavior. and it is running in the more positive side potential from minus 0.3 to 1. So we have chosen this one as the cathode material. For the anode material, we have chosen tungsten trioxide, and which is also prepared using the hydrothermal method. It is in the hexagonal phase. This is the XRD pattern of the WO3 showing in the hexagonal phase, and the Raman peaks match well with the literature, and it shows flex like nanorod like structure. So this is the electrochemical investigation of WD in the same specific electrolyte taking the same proton concentration. And here we faced one issue, that is there was continuous discharge after few number of cycle, say after 30 to 40 number of cycle. Here we can see was quite prominent in the case of HCl. As we are using aqueous electrolyte, so in aqueous electrolyte, a side reaction or splitting of water can occur. So it is leading to HER, hydrogen evolution reaction. So to suppress that, we have chosen one strategy and moving forward with H3PO4, because at higher current density, we could see that H3PO4 shows a better result at a very high current density at 40 ampere per gram. So we have prepared a specific kind of gel electrolyte using PVA, polyvinyl alcohol, because it has very high conductivity as compared to other polymers. So here, after optimization, we took 1:8 weight percentage of the gel electrolyte, and the behavior, the CV profile is similar to that of the aqueous electrolyte, and the GCT, that is the galvanostatic charge discharge profile, matches well and support well the CV profile. And here we could see that it could run for more number of cycle, like for 100 number of cycle, it could go up to 3000 cycle also, but which was not possible in the aqueous electrolyte. So moving towards the full cell setup, we took cathode as VOH and anode as WO3 in different gel electrolyte. At first, we start with 3.75 molar of H3PO4 gel electrolyte, and here we could see that 1:8 was showing better result. So we move forward with 1:8 weight percentage for higher concentration of the gel electrolyte, as we wanted to prepare a kind of a gel in acid kind of solution. So as we were increasing the concentration, we could see that the performance also increased. This may be due to the the H3PO4 PVA gel electrolyte from a interlinked polymer framework, which reduces the water solvation, and reducing the water solvation reduces the degradation of the electrolyte. And in the cross-linking, we could see that more number of ions are present. That is nothing but the charge carrier ions, and we could get more higher capacitance. And here we could run it for 3000 cycles. So one important aspect is the self-discharge part of a battery. So here we again tried with a hybrid electrolyte, taking 9 molar of H3PO4 PVA and 6 molar of H2SO4. And here we could see that the performance was 4 times
Sorry,
of 6 times.
sorry to disturb, Konica. Try to finish within 2 minutes.
Yes, sir. I'm finishing. Yes. So here we could see the self discharge of this three combination, and we could see that for the aqueous electrolyte, it was after 30 hours we could see it self discharge up to 0.2 volt. But for the PVA based gel electrolyte and the hybrid electrolyte, it was up to 0.8 volt. So it reduces the self discharging rate. So what is happening in the discharge mode? Ions are moving from the anode, it is moving towards the cathode, and to balance out, the electrons are moving from the negative towards positive. And in the charging mode, what is happening? The ions are coming out of the cathode and it is moving towards the anode. So here side reaction is occurring. So after few cycles, we cannot move forward. But here what is happening in the cross-linking polymer, we can see that the ions are trapped and side reactions are not happening because it is reducing the water solvation. So here is an application of lighting of this combination, and it could light up to 5 minutes using this electrolyte. So in conclusion, we could see that for H3PO4 is one of the best electrolyte for proton storage in W3 at higher current density. So it could resolve, the gel electrolyte could resolve the problem of long cycle life. And apart from that, the hybrid electrolyte could increase the storage capacity, and we could see that with the concentration also performance was getting better, and the self discharge reduces the the gel electrolyte reduces the self discharge of the full cell.
Project
Thank you.
is synthesis and characterization of carbon quantum dots using multiple fruit extract. Earlier, my study was using only banana leaf extract, but now we have used multiple fruits. Like I would have made it as POBA, pomegranate, orange, and banana, apple. The field of nanotechnology is one of the most active areas of research in modern material science. New applications of carbon quantum dots, nanoparticles, and nanomaterials are emerging rapidly. Green synthesis provides advancement over chemical and physical method as it is cost-effective, environment-friendly, easily scaled up for large-scale synthesis. No need to use high-pressure energy, temperature, and toxic chemicals. CQDs can be used in combination therapy for decreasing antibiotic resistance or for their antimicrobial and antioxidant activity. My experimental work, CQDs were synthesized using simple hydrothermal carbon ionization treatment of multiple fruit extract peels. In the beginning, I started studying only with the banana peel, but then as my guide suggested, we used 4 fruits peel, that is pomegranate, orange, banana, and apple. The multiple fruit peel waste was ground well with deionized water. The suspension of this POBA peel, 70 ml, were taken into a 100 ml Teflon-lined stainless steel autoclave and then hydrothermally heated at 200 degrees Celsius for a period of 24 hours. This can be done in the laboratory itself, sir. And we were trying with first 1 fruit and then 2, and then now we have gone to 4 fruit peels. The autoclave was cooled at room temperature. Subsequently, the resulting solution was passed through a mixed cellulose membrane with pore size of 0.22 micrometers to remove aggregated particles or dust particles. This gives a clear golden brownish solution. The obtained CQDs were kept in a refrigerator at 10 degrees for additional measurements. This is the multiple fruit peel waste, which I have taken the photo, and the fruit multiple fruit extract, 24 hours heating for 200 degrees Celsius, and we have got a golden brown color solution, which we believed to contain CQDs. And further investigation using UV visible spectra of CQDs from POBA. The UV visible absorbance curve of the synthesized CQD shows the broad absorption ranges at 270 and 380 nanometer in the UV region, which are correlated to the typical pi to pi star transition band of the aromatic C double bond C sp2 hybridized orbitals and N to pi star transition band of the carbonyl group and sp3 hybridal orbitals for any functional group on the surface of CQDs, respectively. XRD pattern, mainly we went through it to find out whether we have some graphic district structure. The XRD spectrum reveals the presence of 3 dominant peaks around 22.8, 42.5, and 53.7, which are credited to 002 plane, 100 plane, and 004 lattice spacing of carbon-based nanomaterials, respectively. The peak positioned at 22.8 corresponding to the plane 100 with an interlayer spacing of 0.37 nanometer. This 002 plane interlayer spacing is vaguely superior than that of typical bulk graphite, which is just 0.34 nanometers. This confirms the synthesized CQDs predominantly with the graphitic structure and has a small amount of amorphous carbon. So the graphitic structure will be further investigated through Raman spectra, sir, that I will be presenting in the next slide. FTIR spectrum of CQDs from POBA. The synthesized CQDs possess a broad band around 3,400 per centimeter assigned to combined OH and NH stretching, which can happen in the layers. The sp3ch stretching band observed around 2830 and 2950 per centimeter, and C double bond O stretching vibration of the carboxylic acid appears around 1720 per centimeter. The absorption peak around 1590 per centimeter indicates the presence of C double bond C stretching vibration of aromatic rings, and peak at 1450 per centimeter corresponds to CN stretching vibration, which indicates the presence of nitrogen element on the surface of CQDs. This is the TEM image of CQDs from POBA. The particle size range within the limits of 4 to 6 nanometer, and the average diameter of particles was about 5 nanometer, suggesting the particle is in narrow distribution with a spherical shape. A single contiguous crystalline phase with a lattice fringe spacing of 0.21 nanometer corresponding to the lattice fringes of typical graphene facet 100 plane. Raman spectrum of synthesized CQDs 1366 per centimeter, 1586 per centimeter, where we are referring to D band responsible for the disordered surface and G band attributed to the sp2 carbon networks from the CQDs, which suggest there is a formation of crystalline structure of graphite. The intensity of D band is lower than that of G band, suggests the good graphitization of synthesized CQDs. So my conclusion is, in summary, CQDs have been synthesized through a simple hydrothermal carbonization method in an environment-friendly manner with the use of POBA peel waste as both carbon and nitrogen sources. The resultant CQDs had near spherical morphology with an average diameter of approximately 5 nanometer and exhibits an acceptable degree of graphitization. CQDs have good biocompatibility and excellent fluorescent stability, which are ideal candidates for biomedical applications. These results may motivate the cost-effective, green, and sustainable synthesis of highly fluorescent, multifunctional carbon-based nanomaterials with various future potential applications such as biomedical and optoelectronic applications.